So yes, hello everyone. So we are starting the course on measure theory by NPTL, and this is the discussion on week zero of the course. And this week zero is all about the review of the basics. So we look at four major things that we'll use throughout the course. Most of you must have definitely studied this during the basic course of the analysis, or even before that, just before the analysis. If anyone has studied foundations course, people must have taught you this. But nonetheless, let us look at these four things. So the first one that we are going to look at is the Archimedian property. Archimedean property of natural numbers in the set of real numbers. So everyone might know that these are blackboard characters, and we usually use them to denote the known sets. Right? These are called blackboard characters. Similarly, we also have this Z and then Q, etc. The second thing which we want to look at is uh, the principles of mathematical induction. Mathematical induction. There are two equivalent statements. One is called the strong induction principle, and the other is called the weak induction principle. We'll look at the statements and will not give the proof of equivalence. The proofs can be easily found in any real analysis book. The third thing which we will look at is the injectivity and surjectivity of functions. Injectivity and surjectivity of functions. And the fourth thing which we will look at are set operations, especially infinite union and infinite intersection. So, so okay, let us begin. So, what does the Archimedian property tell us? It says that the set of natural numbers is unbounded in R. Archimedean property. Again, this also has two equivalent statements. One simply states that n is unbounded in R. And the second one says that you take any real number y and you take any positive number x, we can always find a natural number such that n times x is bigger than y. So the equivalence is easy to see, right? Because if you assume 1, then suppose 2 is for, right? A short idea of the proof here. Why are the equivalent? So assume 1, but not 2. So that would mean, so if 2 is wrong, then which statement is correct? It means that there is some y in R, there is some y in R, and there is a x positive, such that for each n, nx is less than or equal to 1. But then this is same as saying that every n is less than or equal to y by x. And I know that y by x is a real number. So this is that natural set of natural numbers is bounded in R, which is a contradiction. So if I assume 1, then 2 is 2. Similarly, if we assume 2, then what we say is that you just take x equal to 1. Then it says that for each y in R, we can always find some n such that n is bigger than y. And this is precisely stated. It is not bounded. So this was about Archimedian property. And we'll see the use of this is especially the infinite unions and intersections. The second thing which we wanted to see is the principles of mathematical induction. So first let us see the weak induction. The principle of mathematical induction. So what it says is that let A be a non-empty set. Let A be a non-empty set inside N, inside the set of natural numbers. Suppose the following two conditions hold. First one is 1 belongs to A, and the second one is if N belongs to A, then N plus 1 also belongs to A. Then the conclusion is that A must be all of them. Again, this is quite intuitive, right? What we are saying is 1 is already inside A, and given the condition that whenever some natural number is inside A, the next natural number is also inside A. So if 1 is inside A, then 2 is inside A, and 3 is inside A, and then so on. So basically all of natural numbers are inside A, and therefore A is all of them. And then we have a stronger version of this, stronger in the sense that the assumption is stronger. Strong principle of mathematical induction. Just a moment. So what this says is, again we have the same first assumption that suppose we have a non-empty set A inside N. So when I say inside N, it means that A is a subset of N. And suppose that 1 is inside A. Second condition is that given that 1 up to N, all first 10 natural numbers are inside A, then N plus 1 is inside A. If these two conditions are true, then we have A must be all of it. Again, this is also very intuitive because we are starting with 1 is inside A, then the singleton set 1 is a subset of A, therefore 2 is inside A by the second assumption. And now the set 1 comma 2 is a subset of A, so 3 is inside A, and then you continue this, all of natural numbers will be inside. So now let us see some applications of this. You may find this some assignment problems as well, and I would rather recommend that you try them first before looking at these proofs. So let us look at first example. So we want to know what is this sum, 1 square plus 2 square all the way through it. So we know the formula already, right? That summation I square, when I from 1 to n, it gives us n plus 1, 2n plus 1 upon 6. So why is this so? So let me just write this as my claim. So to see that this claim is true, we will use the induction principle, and here we will use the weak induction. We will use weak induction. So how to do that? Let us first check that this formula is correct for n equal to 1. For n equal to 1, summation I from 1 to 1, I square is just 1, and n plus 1, 2n plus 1 by 6. This is what 1 into 1 plus 1 is 2, and then this 2 plus 1 is 3 upon 6, which is 1. So, okay, at least for n equal to 1, this is correct. This claim is. Oh, yeah. So I should mention it here that I am writing this set A as the collection of all natural numbers such that summation I from 1 to n I square is n plus 1, 2n plus 1 by 6. I want to prove that A is equal to n. So there are many things that we need to prove if we want to use induction. One is that A should be a non-empty set. Second is 1 should belong to A. And the third one is whenever n is inside A, n plus n is inside A. So clearly A is non-empty because we have proved that 1 is inside A. So write it is 1 is inside. Therefore A is non-empty. And we already have assumption 1. Now let us assume that there is some n in natural number such that n is inside. Suppose n is in A. What does this mean? It means that summation I from 1 to n, I square is equal to n plus 1 to n plus 1 by 6. We know this to be true. Now we want to prove the same formula for n plus 1. So let us look at, let S be some I from 1 to n plus 1 I square. This I can easily write some I from 1 to n I square plus n plus 1. That is just I am using associativity of addition, nothing more. And I now know the formula for the first term. This is n plus 1 to n plus 1 divided by 6 plus n plus 1. Okay. Yeah, sorry. So n plus 1 square. What I will do is let us take n plus 1 common and then 6 also let us take common. So it takes n into 2n plus 1 plus 6 times n plus 1, which turns out to be n plus 1 by 6 into 2n square plus n plus 6n plus 1. So maybe I'll write it as 7n. And okay, let me just denote this by say equation 1. On the other hand, what we want, so we want that the final thing should be n plus 1, n plus 1 plus 1, 2 times n plus 1 plus 1 by 6. And this is what? This is n plus 1, n plus 2, and then 2n plus 3 divided by 6. So notice that we already have n plus 1 from here. We have 6 from here. Somehow we need to get n plus 2 and 2n plus 3. So for that, what we will do, let us try to split this property. So I know that this 2n plus 3, this 2 is going to come from the factorization. Get another mistake, this should be 6. So how I will factorize? Let us write 7 as 4n plus 3n. And then let us see what happens. So this is now equal to n plus 1 by 6 into 2n square plus 4n plus 3n plus 6. Now what I can do? I can take something common here. I can take 2n common here. This becomes n plus 2. I can take 3 common here. This becomes n plus 2. And then I can take n plus 2 together common. So this becomes n plus 1, n plus 2, and then 2n plus 3. And this completes the proof. Right? This directly tells us that A must be all of n, and therefore this formula should hold for every natural number. Okay. So notice that this did not require this stronger assumption that all of the first n natural numbers are inside A. Just the nth natural number inside A could give us that the n plus 1th natural number is also inside. Now let us look at another example where we'll need to use this strong induction. So for that, let me just define a recursive sequence. What I will do, let us define x1 as 3, x2 as 5, and for n bigger than or equal to 3, let me define xn as 3 xn minus 1 minus 2 xn minus 2. So with this definition, now directly from this thing, we cannot really guess what is going to be the formula for the general entry. If we try to substitute n minus 1 and n minus 2, then these things are just going to be larger and larger, and we cannot really simplify. So what we'll do, let us try to compute the first few terms, maybe up to 5 or 6, and then we'll guess the formula. So let us compute x3. x3 by definition is 3 x2 minus 2 x1, which is 3 times 5, 15 minus 2 times 3, 6, which is 9. x4 is 3x3 minus 2x2. So 3 times 9 is 27 minus 2 times 5 is 10. That is 17. What is x5? So this is 3x4 minus 2x3, which is 3 times this is 51 minus 2 times 9 is 18. So this is going to be 33. So if we notice, like we should be able to notice a pattern here clearly. This is 8 plus 1, which is 2 cube plus 1. This is 16 plus 1, which is 2 to the power 4 plus 1. And this is 32 plus 1, which is 2 to the power 5 plus 1. So what we claim? We claim that the nth term in this sequence claim is that xn is given by 2 to the power n plus 1 for every. So now it is easy to see that x1 and x2 already satisfy this thing. And the thing is, we cannot really use x1 and x2 here because we don't have a recurrence relation between x1 and x2. So we'll have to use the induction from 3 onwards. So what I will write is, again, let the set A be given like this. Fraction of all n such that xn is 2 to the power n plus 1. Then I know that this set 1, 2, 3, this is a subset of A, and hence A is non-empty. Moreover, I know that 1 also belongs to A, so no issues. Now let us assume that the first n terms are inside A. Assume that 1 up to n, this is a subset of A. What does this mean? This means for every I in this set, 1 to n, xi can be written as 2 to the power I plus 1. That I already know. Now I want to move to the next step. So what is xn plus 1? Xn plus 1 is by definition 3xn minus 2xn minus 1. But now I know that this n and n minus 1, they are both in A. So I have the formula 3 times 2 to the power n plus 1 minus 2 times 2 to the power n minus 1 plus. So this is 3 into 2 to the power n plus 3 minus 2 into 2 to the power n minus 1. So that is just 2 to the power n minus 2. So yeah, change. So notice that this and this together, what they will give? This will give 2 times 2 to the power n, which is 2 to the power n plus 1. And these two terms, they are going to give us 1. So all in all, this whole thing turns out to be 2 to the power n plus 1 plus 1. And therefore, what we say is that n plus 1 is in A. And hence, from the strong principle of mathematical induction, A must be all of it. Okay. So there are a few points to notice here. One is that we cannot use the weak induction. At least we cannot use it directly. Why we cannot use it directly? Because, here we are using the fact that both n and n plus 1 are there inside the set A, so that we can directly use the formula. This n and n minus 1. We are using the formula, so we want both of them to be inside A. If you want to use the weak induction principle, then we have to argue that somehow we have n minus 1 as well inside A. So yeah. Now, okay, so these were some applications of this weak induction and strong induction, and you can try doing more. You can sort of, perhaps this could be an exercise. You can try finding the formula for the cubes. Now let us move to the functions injectivity and surjectivity. Again, I will just give the basic definitions and just we'll look at a few examples before we move on. So what is injectivity? A function f from set A to another set T. This is injective. Often it is called as 1, 1. If whenever f of x1 is equal to f of x2, then x1 is equal to x. So what it means is that suppose we have these two sets A and B, and then there is a function in between. It maps some points to some other points. Maybe it goes here, and this one goes here, and this goes here. Okay, it cannot happen that 2 points go to the same image. So this thing is not allowed. If we are to say that the function is injective. But what can happen is there is some point which is not the image of it. So this is always allowed. The only thing not allowed here is that 2 different points cannot go to the same image. The second thing which you want to look at is surjectivity. What does surjectivity say? A function again from one set to another is surjective, also called onto, if for each y in the other side set B called the codomain, we can always find some x in A such that y is the image of it. So here pretty much this condition which I mentioned above is not allowed. That means again you take two sets. You take any point here y, you can always find some x which goes to y. But here, this can happen. There is some other point x prime which goes to y. So this is allowed. What is not allowed is something which doesn't have an image. This not an image. This is not allowed. Okay. Now, if a function is both injective and surjective, then it is called bijective. It means both injective and. So intuitively, what we say is that if we have a function which is injective, then the sort of number of elements, let me just make it in quotation marks because for infinite sets we don't really have number. So if f is injective, then intuitively, so notice that this is only intuitive. This is not the mathematical definition or anything. Number of elements of A, these are say less than or equal to number of elements of B. Because if there were more elements than B, then we at least 2 elements go to the same element. Right? And similarly, if it is surjective, then we have the other way around. And if it is bijective, then this must be equal. So these bijections are really important in all the studies, right? Because what bijections do is that they sort of identify sets. So bijections identify sets. That means if we have a bijection from A to B, then A and B, they may have some different elements as such, but still we can use A in place of B, we can use B in place of A, it won't matter. So then A is usually it is like this, it is identified with B or B. So now let us look at some examples where we'll see some functions are injective or they are surjective or both or none of them. So let us first look at this function from R to R. Let us look at fx is equal to sin x. So this is the most sort of common example. Right? Now notice that here we have f0 and fi are same. So that means f is not injective. And we also have that fx is never 2, right? Since sin x is always between -1 and 1. So therefore, F is neither not surjective as well. Okay, but if we try to change the domain and codomain of it, then it may become injective or surjective or whatever. So if you look at again from R to say -1, same function. So fx is sin x. If you look at this, then f is surjective, but again not injective, right? The same counterexample, right? Not injective. And if I change the domain a bit, say if I write it from minus pi/2 to pi/2 to R, again fx is sin x, then this is injective but not true. Injective but not surjective. And if I change both, so from minus pi/2 to -1, that is a bijection. And some other examples which everyone must have already seen is f from R to R, say f any linear function, ax plus b, where a is non-zero. So this is a bijection. And it is easily provable, because if ax1 plus b is ax2 plus b, then that b cancels and a is non-zero, so a also cancels. X1 equal to x2. And if I start with any y in R, just look at y minus b by a. So that is the pre-image of y. So this is a bijection. The last example, or perhaps the last example in this discussion, let us look at e to the power. So this is a classic example which is injective but not surjective, because now f is always positive, which would mean that f is not surjective. In particular, 0 does not have a pre-image. But using some techniques of analysis, we see that this exponential map is actually invertible. And invertible in the sense that if I restrict this codomain to 0 infinity, then this is invertible with the inverse given by law. And like to prove this, we in between prove that exponential map is invertible. Okay. So this was all about injectivity, surjectivity, and bijections in general. Now what we want to look at is set operations. So give a little set operations. So we know the basic set operations, right? Union, intersection, and complement. So what does this mean? Given two sets A and B, this is defined as the set. Collect all those x. Oh yeah. So I need a universe. Right? So in this discussion, x is our universe set, which means that nothing can go outside of it. Or whatever points we'll consider only the points of this given universe. So the union is defined as all those x, such that x is either in A or x is in B. It can very well be in both, but yeah, we want it to be in one of them. The intersection of two sets is defined as all those x which are in both, and x is in B. And this complement, so given A, the A complement written like A superscript C, this is defined as the collection of all x such that x is not. So there are various laws corresponding this. One of the laws that is frequently used is the Demorgan's law. What it says is that if you take the complement of union, then it becomes intersection of the complements. And if you take the complement of the intersection, then it becomes the union of the complements. And then there are other laws as well, law of excluded middle, and like if you union of A and A complement is all of X, intersection of A and A complement is empty, and so on. Yeah. So what we are interested in is what happens if we start taking infinite unions and infinite intersections. So suppose we have, again, this X is the universal set. Suppose we have a collection of sets A1, A2, and so on. Right now I am enumerating it by the set of natural numbers. Suppose these are subsets of X. I want to know what is this union. Yeah. So by definition, it is collect all those X which are at least in one of the AIs. X is in AI for some. So here there is a thing to be noticed that when I write this 1 to infinity, this is just a symbol. It should not be treated as a number or it is only a symbol. And what it means is that you start taking the union, you take A1 in union with A2 and you take A3, the sets will never end. And similarly, we have this intersection 1 to infinity AI. Yeah, just a matter of notation. Sometimes it is written like this as well. I in N AI, and this will be written as intersection I in N. So these are seen, and they are defined as collect all those X which are in all of AI. So X is in AI for each L. For each. So notice that here I have written for some, here I am writing for every. Okay. So how to find these? Let us see some examples. And especially when dealing with this type of universal intersections, we are going to use the Archimedian problem. Let me just give perhaps two examples. Let us try to find what is the intersection of minus 1 by n to 1 by n. Again, this is a very classic example. Study the Archimedian property. I want to know what. So first case is the first question should be whether this is empty or not. So one can very easily guess that 0 always belongs to minus 1 by n to 1 by n, right, for each. That means 0 is in the intersection. Minus 1 by n. Or, this is same as saying that this intersection is not. Now, what is the next question? The next question we should ask is whether this intersection is exactly equal to singleton 0. Or the equivalent question is, are there any other points of real numbers which are inside this intersection? So the question is, are there other real numbers? So when I say other real numbers, it means other than 0. I've already proved that 0 is inside this. In intersection minus 1 by n to 1 by n. So let us see. Suppose with some real number, let x be in R between 0. So I'm allowing any real number, but I am not allowing 0 for the time being. Then what will happen? See, mod x is bigger than 0, right? Because x is not 0 and mod x cannot be negative. So mod x is bigger than 0. So by the Archimedian property, there is always some n such that n mod x is bigger than 1. Or what I should write is mod x is bigger than 1 by n. And if this is true, then this is same as saying x is not in minus 1 by n to plus 1 by n. Therefore, it is not in the intersection. That means you take any other real number other than 0, this is not going to be in the intersection. And hence this intersection is just singleton set. And similarly, we can prove that in fact the closed intervals also satisfy the same thing. So if I look at closed minus 1 by n to 1 by n, this is still going to be singleton. No other part. And so intuitively, when this true, we should always try to make diagrams as much as possible. So first one would be minus 1 to 1. The second one would be minus half to half. The third one would be minus 1 by 3 to 1 by 3. And then so on. This just keeps on shrinking. So minus 1 by n to 1 by n. So if I take any other x other than 0, I mean, so if x is somewhere here, I can always find some even bigger n for which, I have a still smaller interval. So x comes outside that interval. Now, okay, so this was about infinite intersections. What about infinite unions? So let us try to see what is this union. Closed interval. Or okay, we take. Let me take minus n and minus n. Okay. So okay, let us try to draw a diagram first. Let us see what is happening. So this is 0, this is 1, 2, and so on. On the left hand side, we have minus 1, minus 2, and so on. What I want to do, I want to look at these intervals. So minus n, but here I cannot use really. Okay, I can use that. So okay, for n equal to 1, what I have? Minus 1 to minus 1 plus 1, that is 0. So I have this interval. Then for n equal to 2, I have minus 2 to minus 2 plus 1, that is minus 2 to minus 1. So I have this interval. Then I have this interval, and this continues. Okay. So what does this say? If I take the union, that means I am taking all those real numbers which are in at least one of these. So the guess is that this whole non-positive real line is going to be this union. So our guess is union of minus n plus 1. This is equal to minus infinity comma 0. So to prove that these two sets are equal, again, what we need to do, we need to prove that they are subsets of each other. So you take here anything. So one way is easier because if I take an x here, minus n plus 1, then this means x is inside minus n naught plus 1 for some n. And if n naught is in natural numbers, then I already know that minus n naught plus 1 and this is less than or equal to 0. So therefore, not x naught, only x. So therefore, at least this subsethood is clear. No issues in proving this subsethood. What about the other way around? So if I take x in minus infinity to 0, then what will happen? I want to prove that there should exist some n for which x is inside the particular interval minus n comma minus n plus 1. So again, okay, so let us try to see what it means. So to prove that there is some n such that x belongs to minus n plus 1. But this is same as saying minus n is less than or equal to x. And this is less than or equal to minus n plus 1. Or like this is same as saying that n minus 1 is less than or equal to minus x. And this is less than or equal to n. And this can always, right? This is always. This is possible because the Archimedian property says that there exists some n such that n is strictly bigger than x, and therefore we can find the minimum such n. So let n naught be the minimum such n such that n is bigger than x. That means n naught is bigger than x, but n naught minus 1 is not bigger than x, is less than or equal to x. And therefore x belongs to minus n naught minus n naught. Oh, yeah, I mean to say minus. Even here it should be minus. Okay. Oh yeah, but we have used here something called as the well ordering principle. That also we use quite frequently. What it says is that every non-empty subset of natural numbers has a disk. Every non-empty set of natural numbers has a least element or has a minimum. And one can see that this is actually equivalent to the principles of induction. Equivalent to the principles of induction. So for a proof of this, I don't know a lot of books. So yeah, one book in which you can find this is a foundation course in mathematics by S. Kumar. So all right, this was all about the basics that we'll be using, and especially this what we say infinite unions and intersections, or in general arbitrary unions and intersections that we are going to use in week 1 when we'll define sigma and lambda. Okay then, thank you.